So, with the repeated prisoner's dilemma, a game that we'll spend some time discussing today, prisoner's dilemma repeated. Here is the trick. Maybe let's start by recalling what a prisoner's dilemma is. So, what are the criteria which allow us to call a game a prisoner's dilemma? It should be a game where players have two strategies. Players have two strategies. Typically, we would call them typically the strategies would be called cooperate and defect. So betray the other player's trust. One of these two strategies is dominant. Again, typically it would be the strategy to defect. That means, if you think about it, that that cooperating with the other player is never a best response, right? If defecting is the dominant strategy, then cooperating is the dominated strategy, which means it never gives you the higher payoff regardless of what the other player is doing. So you should never cooperate, right? It's already some conclusion that you can draw. And indeed, the one important thing here is that playing the Nash Equilibrium, which means playing the dominant strategies, gives less utility, gives smaller profit than both, let's say, than all players, because it can be more than two players in such a game, than all players playing their dominated strategies. So after all of these additional reservations which we added, so we added the titles of the strategy, cooperate and defect. We said that the dominant strategy was to defect. Here, if we translate this third element, the third criterion, then what it should mean is that mutual cooperation makes players better off than mutual defection. So if they cooperated for some reason, if they somehow managed to, then they would get higher payoffs than the ones that they get playing the Nash Equilibrium. In this situation, all of them defecting. And this motivates the interest that scholars, game theorists, but also social scientists have in prisoner's dilemma games. Basically answering the question where the players, under which conditions the players would be able to cooperate is very important if you want to study cooperation, right? And there is also a very strong normative reason for us to want to learn the answer to that question, because if it would be possible to somehow design social interactions so that people would cooperate more often, despite the fact that they would rather prefer defecting because that's their dominant strategy, then we would have a better, wealthier, happier society, the society which would have more trust between its members and which would be much more productive. So if we could find a way to make people cooperate in a prisoner's dilemma game, then that would be a big deal, right? Then we would just go out in the streets and just tell people, okay, now we know what we should do. This is how we do it. This is how we cooperate. Some people had some hopes on repetition. So some people thought, okay, if we make the prisoner's dilemma repeated, then maybe it would change players' behavior. However, this is what they found out. So let's have a look at just some game, which is a prisoner's dilemma. As you remember, it's a simultaneous move game, so we'll use a matrix to draw it. In this game, there are two players. They could be more than two. That's really not very important, but for simplicity's sake, we'll just think that there are two. Let's call them first and second. And they have two strategies each. So, we start putting together a prisoner's dilemma. So we start following this criteria. Both should have two strategies. One will be called cooperate. Another one will be called defect. So we'll just call them C and D. And we'll use small letter C and small letter D for a second player to distinguish between the names of these strategies. And the payoffs that they get from defecting are always strictly better than the payoffs that they get from cooperating. So for instance, the first player, if she defects, she gets 3, whereas cooperation would give her only 2. And if she defects against a defector, she gets a 0. But if she would try to cooperate with a defector, she would get a -1. So you can see that it's always like this. 3 is greater than 2. And 0 is greater than -1. And the same payoffs work for the second player. So she gets a 2 if she cooperates with a cooperator, but she would get a 3 if she defected, if she betrayed a cooperator. And 3 is strictly better than 2. And if she cooperates with the defector, she gets -1. And she'd have a 0 if she defected against the defector. Again, it's strictly better to defect. And from here we can see the only Nash equilibrium in this game, this one. And you can see that if the players were playing their dominated strategies, then they would get 2 each, and here they get 0 each. So it's it's not Pareto optimal that they defect. However, that's what they should do if they're rational. If we repeated this game, for instance, twice, right, then we would take this matrix, and from each of its cells, each of its outcomes, we would draw 4 possible developments, 4 possible matrices, which would look exactly like the one that we have already drawn. So there would be these 4 matrices. That's one way to model it. And of course, you know what these other matrices, how these other matrices would solve, right? Because given that they are exactly the same with the one in the middle, with the black one, the single possible Nash equilibria in these 4 subgames would be the ones where players defect mutually, right? Another way for us to draw this game would be to draw a tree, something we could also do. So this tree would look like that. There would be two strategies for the first player. Second player sits in this information set and also has two strategies, cooperate or defect. And then from each of the four terminal nodes in this first stage of the game, there are similar trees growing, right? Something like that. And of course, they each have these information sets, because again, in the second stage, the second player does not know what the first is doing. The first does not know what the second is doing either. And there are some payoffs. If we were to solve such a game, then we would have to write the payoffs here in the very end of the game. For instance, if we look at this particular development, the players start cooperating and they go on cooperating till the very end, then their payoffs would be 2 for the first round plus 2 for the second for the first player and 2 plus 2 for the second player. So they would both get 4, right? However, in this second stage, there would be strong incentives for the players to defect, because if just one of them defected against the other one, for instance, imagine that the second player is defecting, so the game unfolds as follows. They start cooperating. First cooperates and second defects. In this particular development, the payoffs would be 2 for the first from the first round minus 1 for the second, because the first here cooperates against the defector, and for the second they would be 2 for the first round plus 3 because she defects against the cooperator, so it would be 1 for the first player and 5 for the second. And in all of these other how many 14 possible situations, which we will not go into detail of here, it always proves strictly better for the player to defect, both against another player cooperating with her or defecting. That's because in each of these subgames, here and here and here and there, in each of the subgames, it's a dominant strategy to defect. So if we would imagine that such a game would be repeated for, I don't know, like 10 times, the prisoner's dilemma repeats 10 times, then in the end, in the last round, in the 10th round, we would observe this last round that we have just drawn and surrounded with this, circumscribed with these green circumferences, with these green rounds. And in this last round, they would defect. And if we started solving it by backward induction, so we looked at the last round and then the nines and then the eights, etc. In all of these rounds, they would defect and defect and defect, and then in the very first round, they would defect again. In the last round, they play dominant strategy. That is defect. Defect. And so they do in all of the other rounds. So when you start repeating the game, however many times you repeat it, so here, for instance, we repeated Prisoner's Dilemma twice. This is what we got when we repeated it twice. It does not change things, right? People still defect. People still betray each other. That's not the result that we wanted to find. So let's try something else.